Hi students, welcome to today's lecture on compiler design. In our previous class, we have discussed about introduction to language processing and also the structure of compiler. And today, we'll cover evolution of programming languages, science of building a compiler, application of compiler technology, and some programming language basics. These are very basic concepts. I hope every one of you know at least 75 to 80% of these topics already because you learned some programming languages in your previous semesters. Okay, I'll quickly go through all these fundamentals that are not actually so important for your end examination point of view. But anyhow, we'll cover all these topics. The first topic we will cover is evolution of programming languages, where it was started and what is today's scenario. So the evolution was begin in 1940 with the machine language invention. Uh, they are called as first generation languages. So the evolution began with first generation languages, which is machine language, which is comprised of zeros and ones only. That means the programmer, if he wants to write a program, it should be in terms of zeros and ones only. Everything will be written in machine language. Everything will be written in zeros and ones only. So the first generation computers are very limited in computations because programs are not able to write large programs using machine language because it is very difficult to identify uh, the errors in the machine language, and also writing the machine language programs, the large programs, is very difficult as the programmer need to remember every command or every instruction in terms of zeros and ones only. So that is the biggest difficulty faced by the programmers in first generation languages. Coming to second generation languages, uh, programmers use it to write the programs with the help of a set of mnemonics. Mnemonics are nothing but some commands which are written in high level language or some general languages that is used by humans. So, for example, to add any two numbers, the programmer may write add a comma b, saying that the numbers stored in a and b will be added together. Right? So, in second generation languages, programmers felt a little bit easier compared to machine language as they replaced the zeros and ones with a set of mnemonics. Then the capability of these assembly languages, again dependent on the corresponding assembler, based on the number of mnemonics available in the corresponding assembly language. Assembly languages are different for each processor in those days, so you need to define an assembler for every ground level processor set. Okay. So it is easy to write programs in assembly language compared with machine language, but not too easy. Programmers still have a lot of problems. It is difficult to identify the problems, errors, and then debug the assembly language program. So the third generation languages were evolved, which are called as high-level languages, which we are using now, starting with Fortran, COBOL, Lisp, C, C++, Java, and so on like that. Okay, so high-level languages are very similar to the natural language that the humans are using. Therefore, it is very easy to write programs using third generation languages. And the fourth generation languages are meant for query languages or PostScript languages for text formatting, and some other nomad languages for special purposes. These are actually specific applications or special purpose applications used for fourth generation languages are used for special purpose applications like coding the databases, text formatting, and so on. Many other languages are available, right? And the fifth generation languages are meant for artificial intelligence. So, see, OPS5, Prolog, and so on. Many other AI languages were developed, which are under usage now. Okay, so this is evolution of programming languages since 1940 till now, right? And along with this classification, there is another way of classification available for the languages, which are classified as object-oriented languages and scripting languages. Object-oriented languages are written using C++, Java, C hash, and so on. Many other object-oriented languages are available, uh, which is a collection of objects, which the programs are nothing but a collection of objects and classes. And another classification of languages is imperative versus declarative. Imperative languages specifies how computation should be carried out, whereas declarative languages specifies what computation should be done, but not about how. So the examples are Prolog, Haskell, which are AI-related programming languages. Okay, so the as the number of programming languages are evolving, the need of writing compilers is also evolving. So the impact of this evaluation of programming languages is more on compiler technology also, right? So therefore, it's very important topic. Compiler designing compilers is a very important topic, as more and more languages may come in future also. Right? And when we talk about compiler design, what are the things mm, that we need to learn? The science of building a compiler. So if you want to develop a compiler, what are the things that you need to learn? So first thing we need to understand is uh, we are going to develop a mathematical model. Uh, Therefore, we need some finite state machines and regular expression concepts, as the compiler uses these two concepts in the first two phases of its design. So finite state machines are generally used for writing uh, the language recognizes whether a particular string belongs to the language or not. And also the regular expressions are meant for identifying whether it is a valid token in the responding language or not. So these topics we already learned in formal languages and automata theory. And also the other thing is, once we convert that compiler source program into some valid syntax tree with the help of context-free grammars, again, which is part of your formal languages and automata theory. The major step afterwards is going to be optimization process. The optimization process is very important because the efficiency of the compiler that we are going to design depends on how well we implement these code optimization techniques. So as I said, there are two types of code optimization techniques available: machine independent code optimization techniques and machine dependent code optimization techniques. Okay, right. So while designing or while optimizing the intermediate codes generated by the analysis part, one should remember that the compiled program's meaning should not be changed by your optimization. That means whatever purpose uh, is meant by the program written in high level language, that should be served even if we optimize it. Okay, so that is our first rule. We should be following these four rules, otherwise the compiler may not be efficient. The second objective is optimization should improve programs performance. That means instead of using the line to line conversion, if we optimize the code, the performance of the program must be improved. That is what we expect from optimization, right? And then time required for compilation should be reasonable. So because we are using another step over here, additional step over here as optimization, the total compilation time should not be uh, too vulnerable. So it should be reasonable enough, the time required for that optimization process. You should not spend too much time for optimizing, even though it produces the best compiler, right? So time required for compilation should be reasonable enough. And finally, managing management of engineering effort is a must. So after compiler is designed successfully, managing it is also should be easier enough. Okay, so that's what we expect from the compiler design perspective. So the science of building compiler requires two major knowledges for the people. One is about the mathematical models or mathematical concepts related to this compiler design, and the other one is optimization techniques related to how well we can design the compilers. When coming to this applications of compiler technology, there are we all know that the main purpose of compiler is converting or translating a high-level language, a given high-level language into low-level language. But in addition to that application, there are many other applications that can be used under compiler technology. Right. Well, let us have a look at these applications, other applications. So the first application is implementation of high-level programming language. This application we all know because whenever you design a high-level programming language, you require a compiler for that high-level programming language, which translates the given high-level language into low-level language, right? So this is the first application of any compiler design. We already know this, okay? And the second one is optimizations for computer architecture. So computer architecture is nothing but the way the computer processes, the CPU, the number of processors available in your computer, the processor architecture, the number of registers available for processing purpose, and so on. Many other architectures will be there. So when we talk about this computer architecture related to this, the compiler uh, will be looking at two things in a particular computer, whether it is processing a parallelism and what kind of memory hierarchies are used in the computer. Because based on this, we can design efficient compilers also. So what is meant by this parallelism and memory hierarchies? Parallelism is actually executing more than one instruction at a time. That is what parallelism is. It can be implemented at two levels. One is instruction level and the other one is processor level. Most of the computers implements this parallelism. Basic computers implements this parallelism at instruction level only, which means executing multiple operations at a time with the help of a single processor. That is generally called as multitasking in our single processor computers. And the processor level, when your computer contains more than one processor, different threads of the same application runs on different processors when your computer supports multiple processors. So this parallelism can be achieved at two levels: instruction level and the processor level. Instruction level, executing multiple operations at a time, but generally it is done with the help of time sharing machines. And the processor level uses different processors to execute the same application with the help of several threads. Most of the microprocessors exploits this instruction level parallelism, as it contains only single processor. And also the most advanced computers which possess more than one processor may implement that process level parallelism. Okay. And then the second part is memory hierarchies. Uh, this concept is also known to you. You may probably you read this in computer organization. In a single computer, if you look at the types of memories available, uh, you will understand this memory hierarchy. There is RAM, there is hard disk, there is a cache memory, there is a register memory. So all these are different types of memories available. Each memory is different in their processing speed and size, and so on. So if your computer contains different levels of memory with different speeds and sizes, uh, then based on this memory hierarchy also, the compiler must be properly designed. So if your, for example, say if your computer contains more number of registers, then the optimization, while optimizing the intermediate codes, the compiler may utilize more registers for writing the codes. Okay, so that depends. Memory hierarchy is also a consideration while converting your high-level programming to low-level program. So this facility is actually used by the advanced computer architectures. It is evolving like that by keeping this compiler also as a view for developing new computer architectures. And the third application is program translation. Program translation is actually compilers converts high-level languages into low-level languages. That is called program translation. But this translation may not occur at program itself. There are other techniques also which are called as binary translation. Binary translation is translating binary code of one machine to another machine. For example, maybe uh, in a particular computer, according to that computer's architecture, the binary codes, that is machine language, is generated, and you can use that machine language to run on another computer by converting it into the architecture compatibility of that second computer. So this is called binary translation, involves translating the binary codes of one machine to another machine. Okay, there is no need to write the program again. There is no need to compile it again. It is just conversion of binary codes to binary codes. So this is possible with the binary translation, where compiler technology is again used. And hardware synthesis is generally used for designing hardware circuits, which are called as RTL scripts. Converting these RTL scripts into uh, gates, which are then mapped to transistors and finally to physical level, is also require a certain kind of compilers. So this is also one application of compiler technology, as we are writing the instructions in RTL language, where these RTL instructions are converted into gates and then to finally into a physical circuit. The example languages are VHDL and Verilog, which are well known to EEE and ECE students. And finally, database query interprets. When we write database queries, which consists of relational operations and Boolean operations, they are actually converted into the corresponding database language interpreters for querying the corresponding database. Okay, so generally query is nothing but a set of predicates which are then converted into a uh, valid query which retrieves some information from the database, right? So there also, because we are writing the queries in high level language, we require that the high level language is converted into a set of valid predicates so that the information is retrieved properly. There also conversion is required, so we can consider it as a application of compiler, right? And then another application of compilers is software productivity tools. So when we design a software product, the important thing is it does not contain any errors. So it is possible that a program may contain an error if it is not properly tested. So the software productivity tools help us to identify these errors. For example, one such tool is data flow analysis, which identifies the possibility of errors, because it's not possible to identify every error in a particular program. So data flow analysis helps us to generate the possible errors by checking the data flow of the corresponding program. Okay, so this is one possible tool which requires, again, the way we design this data flow analysis tool is again uh, reminds us the compilers again. Okay, another one is static analysis tool to find the errors. So this is also an application of compiler. Okay. And these tools are meant for checking uh, types, if there is any type compatibility, and bounds if there is any illegal use of memories and memory management tools, and so on. They can find out, these tools can find out all possible types of errors that may occur in your program. Okay, so with the help of software productivity tools. So these are applications, and now we'll go through some important programming language basics. The first category is static or dynamic distinction. Probably in Java, you might have gone through these two topics, static and dynamic words. You might have heard this. They actually meant for compile time and runtime. So for example, if you consider this static index, it creates a static variable x, which is also called as class variable. During compilation time, it fixes the memory location, which will be used by all the classes that are created in your program, right? If you create a variable called as index, which will be an instance variable that will be created every time when an instance of a class is created. So dynamically it is created, not at compile time. Okay, so this is the first difference you need to understand. And the second difference is environments and states. What does an environment is meaning? Environment is a mapping from names to locations. Names are nothing but the variables or identifiers that we use in our programs, and the mapping of names to locations. Location is nothing but where it is stored. Is nothing but an environment. It varies based on where you write the corresponding variable. That means where you create the variable. If you look at this example, there are variables which are written before this function, which comes under global environment, and a variable which is written inside the function, which comes under local environment. Okay, so this name I maps to a location, global environment, and this name I maps to a location, local environment. Okay, and then state is nothing but mapping from locations to their values, right? So location is nothing but the exact address, and it is measured, the value of this location is measured by the state. So when you say I is equal to 3, it means it is referring to this location I, that is local I. And x is equal to I plus 1, this statement refers to the location I, the global I. Okay, so this is what another thing that we need to remember, because all these topics will be used while optimizing our compiler codes. That's what we are learning here. All these basics will be required there. And then static scope and the block structure. If you look at the following diagram, block is nothing but a sequence of instructions surrounded by braces. If you look at this, there are number of blocks. This is the first block, B1, and then this is the second block, B2, and this pair of brackets refers to block 3, and this pair of brackets refer to block 4. Okay, now uh, when you look at this program, if you see the scopes of the corresponding variables that spans into the corresponding blocks, have a look at this first variable, int a is equal to 1, this one. Int a is equal to 1 is declared over here, therefore it is available in block 1, and also because there is only another block available, block 2. So other than this block, it is available in block 2. Block 2 covers this entire thing. Because it is available in block 2, it is also available in block 3. And then it is also available in block 4, and so on. Okay, so the first one is int a is equal to 1. It is available from block 1 to block 3. So what happens to block 4? Okay, probably this is wrong. It is up to block 4. And then because it is global here, right? It is available here, and also in the block 2, the entire block 2, it is available. Yes. you can write it as b2, b1 to b2. And int b is equal to 1 is again b1 to, yes, these two are correct because those two statements are written at the same block, same location. This is b2, please correct it, b2, right? And then this int b is equal to 2 is available for b2, b3, b4, but not to b1. Okay. And then int a is equal to 3 is available for b3 only, right? And int b is equal to 4 is available for b4 only. So the scope of the variables are confined to the corresponding blocks where they are declared, right? This is what scope, static scope and block structure. Then explicit access control. The fourth one is explicit access control. Probably you know in C++ and Java, the access control is maintained by public, private, and protected keywords. Public means whatever is put under public is visible to all the classes and objects in your program. And the public things are available beyond the corresponding uh, folders also, right? If they are made public and imported into another program. Okay, so private uh, does not provide any access to the private variables. That means when you declare something as private, they are available within the same class only. That means the functions which are declared in the same class where these private variables, private members are declared, can access these private variables. And protected is if you declare something under protected, they are available within the same class and also the derived classes. Private variables are not available for the derived classes also. They are available only to the existing class, right? And then coming to parameter passing mechanisms, there are actually three types of parameter passing mechanisms: call by value, call by reference, or sometimes this is also called as call by address, and call by name. They vary from one language to another language. In C language, there are two types. One is call by value and the other one is call by address. There is no call by reference. In C++, it is call by value, call by reference, and call by address. There are three types. But this call by name is actually a oldest one, which is not available in the recent programming language. This is not available. Only call by value and call by address are available. So to understand what is call by value, uh, the function call uh, will take the actual parameters, which will be copied to the formal parameters with the help of call by value. That means the actual parameter values are copied to the corresponding formal parameters. That's it. Just values are copied, and then onwards, formal parameter names will be used. Any changes made to formal parameters will not be reflected back to the actual parameters. This is what call by value is. In call by reference, we send the address of the formal parameters, which are copied to the actual address of the formal parameters to, sorry, address of the actual parameters to formal parameters. And for then formal parameters contains a pointer to actual parameters. Therefore, whatever changes are made to formal parameters, they will be reflected to actual parameters also. So in call by name, we send the names again, just like in call by value. Call by value and call by name are same, uh, except that the names acts as macros. That means every when you send a name to as a parameter, it will be replaced as a constant throughout the program. Okay, so when this constant value changes throughout the program, it will be replaced again. That's what call by name is. Whereas in call by value, actual parameter values are copied to formal parameter only once, and even if actual parameters are changed later on, they will not be reflected on functions. Okay, so this is not available in the recent programming languages. Only these two, along with call by address, is available. Okay, so this is about parameter passing mechanisms. And the last topic is aliasing. Aliasing is nothing but creating more than one name for the same memory location. Suppose assume that y is an existing memory location, and now I want to use ampersand x is equal to y. That means use the same memory location for both x and y. Whatever, let us say, you know the instruction x is equal to ampersand y, which copies address of y to x, but then this refers to x and y refers to the same location. That means two names are available for the memory location. That is different. X is equal to ampersand y means x makes x declares itself as a pointer, whereas ampersand x is equal to y does not make x as a pointer. X is a name and y is a name for the same memory location. That is the difference between aliasing and pointers. Okay, so these are the basics of programming languages that we need to understand while designing the compilers. Okay, so that's all for today. Let me go through the topics again briefly that we discussed today. I'll quickly go through these things. So we started with the evolution of programming languages, which covered 5 generations. First generation, machine language. Second generation, assembly language. Third generation, high-level languages. Fourth generation, languages for querying, for PostScripts, Nomad, and so on like that. Fifth generation languages are meant for artificial intelligence languages. And there is another classification, object-oriented versus scripting, and imperative languages versus declarative languages, and so on. The science of building compilers requires knowledge of other mathematical models, and also code optimization objectives we discussed, 4 objectives we discussed. And then applications of compiler technology we discussed. The first application is high-level programming language implementation. Second one is changing according to computer architectures, implementing parallelisms and memory hierarchies, and other kinds of translations along with program translations. We discussed about binary translations and also hardware design languages along with database queries, and software productivity tools such as data flow analysis and static analysis, which are meant for identifying the errors in the program. And then we discussed about programming language basics. The first one is static or dynamic distinction. Static is treated as compile time, dynamic is treated as runtime. And then we learned about environments and states. Environment is mapping from names to locations. State is mapping from locations to their values. Based on the global or local environment, the values changes. And then third one is static scope and block structure. Based on the number of blocks and the way blocks are defined, the scope of variables will be identified. And explicit access control with the help of public, private, protected. Uh, and in C language also there is access control with the help of structures and unions. And fifth one, parameter passing mechanisms, call by value, call by reference, and call by name. Call by name is not available in the latest languages. Only call by value and call by reference or call by address is available. And finally, how to create aliasings, which are giving more than one name for the same memory location. So that's all for today's class. Uh, See you again in our next session. Thank you.